My name is Aridaman Singh Chauhan, and today I'll be talking about our project Acoustic Scene Classification that was done by me and my team under the supervision of Ms. Akansha Tyagi. So first of all, I'll give a brief description of the problem statement. So as you know that there is a lot of variation in infrastructure, population density, variation due to different cultural factors and even device resolution when we talk of recording audio signals across various regions across the globe. So this kind of variation in the available data introduces bias, which leads to degradation in performance in deep learning classification models on these audio segments. So this kind of bias necessitates the need of a robust model design to address the above challenge of multiple domains. So our project aims to develop a robust end-to-end acoustic scene classification system which is capable of adapting to these diverse recording conditions. So our targeted dataset was Urban Acoustic Scenes 2020 mobile dataset, which was provided by TK's 2020 challenge. And the recordings are from 10 different European cities across 10 different acoustic scenes and recorded using 4 different devices. So I'll skip the details of those 4 different devices. The dataset covers 10 acoustic scenes, including airports, shopping malls, uh, bus, metros, public parks, etc. And the dataset comprises of approximately 40 hours of data recorded just from device A, along with smaller amounts recorded using other devices. And the audio provided is in single channel 44.1 kHz 24-bit format. Uh, they have also provided us with simulated dataset which was synthesized using recordings only from device A. So I'll give a brief description of the project timeline. So we implemented and compared pre-existing embedding models, including some CNN-based models, including OpenL3, and even transformer-based models like PASST, AST. And using those embeddings, we performed device, scene, and location classification. And we also experimented on those architectures, and we fine-tuned them, aiming for better performance. Then we did some research on some domain generalization techniques, including COBE, COBEC, scatter component analysis, orthogonal projection loss, etc. And we implemented those domain generalization techniques on our various embeddings extracted from those state-of-the-art models for result improvement. And finally, we compared those results and we used the best model to develop an end-to-end pipeline for acoustic scene classification. Now, Vayun will talk about PSST model, which is a transformer-based architecture.
I'll be carrying forward from here on. So this is our first approach, the second approach, in which we use a transformer-based approach. So in this approach, we use basically the audio spectrogram transformer. In this particular method, we utilize an architecture which is directly almost replicates the structure of a vision transformer with a few changes. So firstly, I'll be explaining the structure. So basically, a T seconds audio clip is converted into a 128 dimensional log mel spectrogram with 25 milliseconds Hamming window with a hop size of 10 milliseconds. So this results in a 128 cross 100 times T spectrogram, which is kind of a one-dimensional image, which is then fed into this transformer by first splitting the image into 16 cross 16 patches and with an overlap of 6, or it can be more than that depending on what structure we would want for each patch and how much overlap we need. And then each 16 on 16 patch is then flattened and then deconned and then flattened into a one-dimensional embedding of dimension 768 cross 1 and fed into a linear projection, which further is sent into the transformer. Before that, a trainable positional encoding is added into each of the embedding to retain the positional architecture of the image input, and then it is fed into the transformer, which has 12 attention blocks in this case with one CLS token, which is then later on used for classification after the 12 blocks. Now I'll be explaining why we used the approach of PSST instead of AST. So the problem with AST is that it takes a really high time to get for inference as well as training, because it uses the entire input and does not drop it. So PSST is a paper which was an improvement over the inference time of AST with the knowledge of dropout. So the main thing in the paper was that they achieved using structured and unstructured patch out by dropping randomly or in a structured way few blocks, few patches from the input spectrogram, and then feeding that compromised input into the transformer, thereby reducing the total input patches, and thus reducing the inference time as well as the training time because of the decrease in the amount of patches and the amount of input. The other small change which they made was to separate the trainable positional encoding into deterministic time as well as frequency encodings. Now, the idea as to why we do this is because frequency encodings do not need to be changed, as each t-second variable audio clip is converted into a 128 dimensional Bell spectrogram. But the time encoding, based on the amount of time we have, we can interpolate and then add time encoding respectively. And as well as with the addition of a CLS token, they also possess the DLS token, which is also they call a distillation token. And the final embedding which they get after 12 blocks is the average of the two tokens which they have, which they use for classification later. So firstly, we did some experiments by we chose the base model for our experimental purposes as the PSST SKD P16, which is 16 embeddings, 16 patch out, as well as 128 dimensional with AP486 model, which was pre-trained earlier on the audio set data. Now audio set data is slightly different from DKs as it possesses a lot more data compared to DKs, and it possesses around 527 different amount of classes which basically signify events. Now, events are not directly related to any of the location, scene, as well as device. However, we'll show what the trend of this approach was. So, for the sake of clarities, events could be many different type of events, such as walking, sneezing, and other type of random events. Now, we also used a classification head. Now, in this classification layer, we had a few input linear layers and then finally a classification layer. And once we trained this network by passing each of our data DK's data set inputs through the architecture by getting the embedding and then feeding it to the classifier, which is our DNN, and then training it, we got an accuracy of 76% on scene and 30% on location classification. These are the results. As you can see, we extracted all the blockwise embeddings, which is of the 12 blocks. Once the input is passed into the pre-trained audio transformer, and we plotted the accuracy curve, and as you can see, we reach a local maxima upon increasing, and then we start decreasing. Now this behavior is attributed to the fact that the audio set pre-trained transformer was pre-trained for image for events, I'm sorry, and events are not directly related to location as well as scene or as well as device. So you can see that as the blocks progress, we expect the locational scene, the scene features to go down and the event features to retain. That's why we see a small drop as we go along the blocks. These are the accuracies for device and location. Now, the device is slightly inflated because it was majorly dominated by A, and we even added class weights to decrease the uh, weight of class A and increase the others. However, it was shown that it was still giving quite a good result, which was ideal. And then for location, we could see the same kind of trend as we saw in scene, and the behavior is again attributed to the same property, as location is not directly relational to events, which was what the transformer was pre-trained and was made to do. Then we continued our experimentations. We fine-tuned our model on the DK's dataset which we had, and then we did the experiments in the fine-tuned model. So you can see the fine-tuned configuration patch outs. We used structured patch out in this case, and we used along the patch out in the T direction of 10 and F direction as 5, and we can see that these are the results for our experimentation. As you can see, since we fine-tuned it on scene, it does not decline as we go. It saturates, which is what we would like to see, as it must retain the scene features as we go along the blocks. and location is again almost the same kind of trend, because we were supposed to the we fine tune it for scene, and location is again not directly related to scene, as it does we expect location features to decline as we go. And here you can see that we attained a new max accuracy of 70.242%, which is almost roughly a 3%, 3.5% gain, and location had a slight bump as well of 31.3%. So these are the confusion matrices for the fine-tuned as well as non-fine-tuned model, and you can see for the base model on the left and the fine-tuned model on right. So one thing which we get out of this is that some classes which like airport and stuff, which was not earlier being classified well, is now classified well, and not all classes could be attributed to the same amount of weight, as some classes are much easier to classify. As you can see, in case of bus, there are significant distinct features which the model learned and previously it was able to learn as well. So these were the observations which were made. Then our main goal was to reduce the amount of training time and the amount of time we spent on fine tuning the model, because for fine tuning the model for 10 epochs, it took roughly around 24 to 36 hours for us. And our main idea was not only to increase the accuracy of the model, but also to significantly reduce the training time. And this we could achieve by using algorithmic approaches, which I'll be talking about. And first is the approach of Kobe, which was common orthogonal basis extraction method. So this approach was for betterment of the 768 dimensional embeddings which we received directly after the transformer, and these did not yield very good results, because these were mainly attributed to the fact that the DNN, once the 768 dimensional embedding was passed to the DNN, the DNN itself was able to do the job of what Kobe was meant to do, and thus we could not see much gain out of this. So we moved on to another approach, which was OPL, which was orthogonal projection loss. Now, learning from previous mistakes, which I'll be talking about in the future as well, we used this particular loss directly on our DNN. So first we extracted the features from the pre-trained audio set transformer, and then we sent once we fed the 768 dimensional vector into a DNN, utilized this loss along with the cross entropy loss in the embedding layer, which is right before the classification layer. And we could see that our new embeddings of the DNN embeddings yielded better results, better embeddings as compared to earlier which we possessed. And then having gotten that result, we tried to use linear combination on all the blocks embeddings, because we noticed that in OPL there was a large bump in the middle layers, especially middle blocks. Thus we thought that if we use linear combination, we could get significant results, and we were able to get better results and even surpass the fine tune accuracy. So I'll be talking about it in the future. So first, I'll be talking about a little bit about Kobe. The main idea about this paper was that it wanted to find a common subspace of all the particular embeddings which we possessed. So we made 10 matrices. Each matrix carried all the embeddings of each of the class. Say for example, airport, bus were some of the examples of the scene classes. And then we use common orthogonal basis extraction algorithm as listed here, and we extracted the a bar, which is a common subspace, and then we removed that common subspace from the embeddings to get discriminated features on the 768 dimensional vector. However, this approach did not yield fruitful results, because once we fed the 768 dimensional, as I said before, the DNN was already removing the common subspace from the 768 dimensional vector. Thus, despite removing it and then feeding it, it did not yield better results, because the DNN was already capable of doing that, and thus the results were neither less neither more, and thus we abandoned this approach. Learning from that, we utilized the OPL orthogonal projection loss approach, and we prioritized this time on the DNN training, because directly working on 768 dimensional vector was not fruitful. Thus, we applied this particular loss. What the main idea of this loss is to angularly diverge different class vector embeddings and move together the same class embeddings. and we do that by reducing the dot product of similar class ones to 0, and the distinct class 1 to 0, to 1. I'm sorry. And I'm sorry, we try to get together the same class 1 to 1 and different classes 0. And basically, upon doing this, we got these results as the final results of the embeddings. And I'll tell you a little bit about the plot. So in this plot, you can notice that with OPL, the particular scene accuracy has significantly increased if you look in terms of the central blocks. Now and these results were better for us, as we could then use these particular embeddings as well, instead of just taking the maximum or the best performing embedding. And one more thing I'd like to point out is that using this approach, we were also able to lower the variance of the location and the device attributes in this. So you can see that location, once we fine tune it, the DNN with OPL and without OPL, we could see for if we use those two embeddings for location and device classification, the one once we train it with OPL, the location goes down as well as the device accuracy goes down, which means that the variance or the features of these particular things inside the embeddings of the each particular sample was decreasing, which is what is ideal for us. Here is a visualization of what was the output of all these. Once we used orthogonal projection loss as per the paper, we could see the togetherness of all the points as to arrange them in a line, which was what was perfectly shown in the paper instead of what was earlier without OPL loss, which was a cluster. And we also visualize it using the TSNE plot. And then we use the dot plot of all the particular points as compared to the other, as compared to each other. So we had around 13,000 different samples, and we had a 13,000 across 13,000 metrics, and each particular class was bundled up together. So first 1,300 or something points were, you can assume, was around for airport. And you can see there are squares of similarities, which is because same points, same class points are similar. And you can see one main thing was that if you look at the particular different class dot products, the amount goes down significantly as compared to the without orthogonal projection loss, which was ideal for us, as we wanted to increase the divergence of each particular different class points and get together the same class points. Now we finally use the linear combination approach, in which all the DNN embeddings, which was of 256 dimension in nature, we extracted these embeddings for all 12 blocks, and we use a trainable coefficients, 12 trainable coefficients, and we use a linear combination approach to generate one final 256 dimensional embedding. And then we further say passed it through a classification layer and trained for 600 epochs, and we were able to get the accuracy around 70.99%, which, if you recall, from just pure pre-trained model, we got around 67%, which was therefore roughly a 4% increase. And as compared to the fine tune, which was around 70.42, we got around 0.5% increase. And we have also plotted the confusion matrices as well as the weights. So you can see the last three blocks were given main priority, with the 10th block being the highest.
So, along with PSST, we also used a CNN based model which is OpenL3. Now, OpenL3 is a model which is able to learn both visual and audio semantic information in a completely unsupervised manner. Now, as we know that the classification labeled dataset for audio scene classification is scarcely available, so we developed a technique for completely unsupervised manner training, which is by simply looking and listening to a large number of unlabeled videos. So our model, which is OpenL3, consists of two subnetworks. One is the vision subnetwork, and the other is the audio subnetwork. The vision subnetwork takes a look at the image from the corresponding video, and the audio subnetwork consists of the MEL spectrogram, which is of 1 second and 48,000 kilohertz. Now that it has a window of 0.1 seconds and has a half of window overlap. Now the model is trained pre-trained on audio video data set, which consists of both environmental and music sounds. We use the environmental sound subset for extracting the features. So instead of using both the vision and audio subnetwork, we just use the audio subnetwork for extracting the features of our DK's 2020 dataset for further ASC classification. So what we did for experimentation with the OpenL3 model is that we first fed the DK's clips, which is of 10 second, into the audio subnetwork. Now we set a hop size of 1 second, which makes the audio subnetworks break the clips into 11 clips, of which are of 1 second and which are padded by 0.5 second on each end. Now features are extracted of the clip after each convolution block. So we have 4 convolution block in our subnetwork. So that's why we got 4 features as shown in the slides. Now what we saw that the dimensionality of the initial features that we got from the initial convolution blocks, that is convolution 1 2, was very high, and so that would cause a really lot of problem, as the amount of RAM that was required to do computation was exceeding approximately 205 GBs. So we apply some dimensionality reduction techniques on the extracted features to reduce their size. We had some dimensionality reduction techniques in mind, like DNN, average pooling, and autoencoders. We tried all of them, but before we could get results from many of them, like autoencoders and DNN, we got better results from global average pooling, and in much lesser time than autoencoders and DNN. So we went ahead with global average pooling. So what global average pooling does is, so as you can look on the slides, the output of the first convolution block of the audio subnetwork is 128 cross 99 cross 64. So what it does, it converts the corresponding features into 1 cross 64. So what it makes is it makes the one feature cut, restart. So as you can see on the slides, the output of the first convolution block is 128 cross 99 cross 64. So what global average pooling does is it makes the output of that convolution block into 1 cross 64. So it replaces one feature map with corresponding real number, which can be either the average of the entire feature map or the maximum number present in the feature map. We went ahead with the average one, as it gave better results. And now for further ASC classification, we use the features that were extracted using global average pooling, and we had each head first trained on for scene classification, keeping the entire audio subnetwork frozen. Now we had classification heads after each convolution blocks. Now after the classification heads are trained for scene classification, the hidden layers of the classification heads are frozen, and only the final layer is trained for location and device classification. Now we also train some completely different heads for device, scene, and location classification. Now we implemented these for ASC dataset and DK's dataset as well. Some of the results on DK's dataset with OPL applied to them. OPL was discussed in PSST as well, so I will not be going over it here. So now we can see that OPL improved the classification accuracy of our model by approximately 1 to 2% or even more in the initial two layers, and higher than 2% in our third layer, and more than 5%, 5 to 6% in our final layer. So we also saw a decreasing trend in our device classification accuracy. That was because our model was trying to learn to classify the scenes better. That would make the device accuracy decrease, as some of the features that are required for device classification may not be overlapping with the scene classifications. So that's why we see a increasing trend, then we saw a decreasing trend and the 28th layer, which is the fourth conclusion block. Plotted the TSNE of the scene classification with and without OPM. So we can see that the embeddings that were given by OpenL3 were not really good, as the features are quite intertwined, and this would make the classification task very difficult. So for PSST, as the initial embeddings were really good, OPL was able to improve the accuracy drastically. But in our case, as the features are really intertwined, OPL is not able to separate them in a good manner. So we have this with the OPL loss applied, and this without the OPL loss applied. You can see the clusters are forming, but they are not that much visible for scene classification. Thank you.
But I'll be explaining the experimentation and extra features which we have implemented. For this, firstly, we had noticed a striking similarity between audio transformers and vision transformers, being that we create patches of the spectrogram and then we further then classify based on that, and then we use our encodings on the basis of that. Furthermore, we also saw that we through papers which we read, we saw that patch out and dropout were quite similar. Patch out being PASST and dropout being a popular technique used in vision transformers. We also saw about self-supervised predictions by masking some patches. This was again a paper on AST, self-supervised AST, which is a similar feature which is used in vision transformers. Furthermore, feature disentanglement is another thing which is also done in vision transformers. So this gave us a motivation to try and go to the basics and start with a vision transformer and build upon that. So for that, we just use a simple clip based vision transformer. For specifically, we used clip VIT base 16. A clip model is ideally used for both text and images, but we used only the image branch and then used those embeddings for our classification. For our training, we use three different dimension reduction techniques, namely no reduction meaning the original embeddings from the clip model. Secondly, we used autoencoding to reduce it to 256 dimension. And thirdly, we also used principal component analysis just for dimensional reduction. After the dimension reduction, we also used multiple classification heads. We used fully connected networks, we used support vector, we used KNN, linear probe, naive base, and on the basis of these combinations, we tried to find the best model which was possible. We found out that the model with for clip using SVM with autoencoding as a classification technique got the highest accuracy, which was 63.3%. This is lower than the baseline model of PASST, which was 67%, which shows that improving on this, we can ideally get a better result. Furthermore, for location and device also, we got accuracy similar to those of PSST. Moving on, this is a TSNE plot. It just shows that the encodings which we received are not that great because of the entanglement of these points. It just shows that we are not able to classify them properly. This is just two of the locations, but adding more locations just doesn't classify as good. Furthermore, from this method, we plotted a confusion matrix. Looking at this confusion matrix, we found out one important inference, which was that high traffic areas cause issues in the classification. For example, airport, shopping areas, traffic areas, and street pedestrian areas, these all misclassify between each other. This just shows us that classifying between these is a difficult task just because of the variance in them. So the solution to figure this out was we create larger clusters. Basically, we do hierarchical classification in which we create larger classes, and then on the basis of once we classify into those larger classes, then we subclassify into the smaller classes. So basically, for example, we have bus, metro, and tram. We group that as transportation. Public spaces like station, shopping mall, and airport, we group them as public spaces, and first we classify into them, and then we classify into the subclasses. This was another idea based on hierarchical classification, which could be useful. Furthermore, we thought of adding metadata, which was basically using speech or song based features for our scene data, which we thought of experimenting.
For example, we use harmonic to noise ratio, we use the envelope, we use chrome features, we use melody, structure, and timbre. We use these features from, we extract these features and then give this metadata along with the original spectrogram. That was the idea. The result of this is that there was no major change, since the neural network itself is able to gain all the required information, and this is not really adding any new information. Another experiment which we had done was data augmentation, since we had initially thought that we were overfitting on our data. So we had done GAN based augmentation. We use spec augment, which is the most popular used, and we use time frequency masking. We use spec augment plus plus also, which is basically applying time and frequency masking in the embedding space instead of the image space. Furthermore, the final technique which we had tested upon was using a branched model. This was the most promising one, in which we take the input and we use two embedding models, embedder 1 and embedder 2. Taking the embeddings from these, we then concatenate them, and then we use a classification head after that. We tried two different things with this. Firstly, we tried making embedder 1 as CNN based model and embedder 2 as transformer encoder model. The reason being, CNN could extract the features in a local space and compare them with the other space, and then transformer, because it can apply its attention and then understand the importance of these features. Doing experiment 1, we did not see any major improvement. So we found out that PSST and OpenL3 had some issues in them. What namely, PSST was able to classify some of the classes accurately, while some not. Some it was not able to classify as good, and OpenL3 was able to classify the ones which PSST failed to classify. So we thought of combining the knowledge of these two models and then using it as embedder 1 and embedder 2, and then concatenating them and then using the classifier. With this, we saw an improve in about 1 or 2%, which was not major. It was after training for a lot of epochs, and we noticed that it was showing some improvement, but it was not a major improvement. So again, we dropped this idea. This was the most promising one. It could probably be improved upon in the future, but as of now, it is not working. So we dropped this, and then this is not included in our final model. So this will be the conclusion, and I'd like to thank you for watching the video. Please like, share, subscribe. Thank you.